Well, hello everyone and welcome. I had it down. It's a lovely sunny afternoon, but it's actually overcast at the minute. But it's lovely weather here in the north of England. I hope all is well with you, and I hope you're ready for some learning on overhead lines. Most of the attendees are based in the UK, but we also have some attendees from Europe and the US. Very warm welcome if you're joining us from outside of the UK. As you can see, we are in an MS Teams meeting. You will notice that your video and microphone is disabled. This is by design, as the session will be presenter-led as opposed to an open discussion. It'd be lovely to have a two-way conversation with a number of people. We're expecting this is just not practical. You can, of course, interact via the chat facility, and I'll explain how to do that shortly. My name is Richard Park. I'm an electrical engineer and I work for Threepwood Consulting as a principal consultant. I'm currently at home in Cheshire, England, and I'm joined by Bill, who's getting ready backstage at his office in Derby. For anyone who hasn't heard of Threepwood, we are an independent electrical power consultancy. We're based in the north of England. And many of our consultants have worked for UK electricity distribution companies. We're heavily involved in the development of electricity documentation, standards, specifications. We've also done a lot of work in electrical safety procedures, for example, developing a procedure for establishing equipotential zones for safe working overhead lines. We also do quite a bit of work in asset management, feasibility studies, network planning. I'd like to thank you for joining, and we want to pass on our knowledge and experience of the subject so that the whole electrical engineering community is better informed in making decisions. Today's presentation will be delivered by one of our associate consultants, Bill Sayre. Bill has 40 years experience in overhead line design, both wood pole and tower lines, up to 400 kV. Bill is chairperson of the BSI PEL 11 committee. That's the committee that oversees standards for overhead line design. Bill is currently assisting ENA overhead lines panel with the development of a new specification for engineered poles. Bill will take you through a technical summary of the crux overhead line design. I hope that's why you're all here. He's going to explain both, why sag and tension are important and why they are the crux of a overhead line design. He'll also explain deterministic calculation and probabilistic calculation. So before I hand over to Bill, just some housekeeping. As I mentioned, we will have questions at the end. If you just go to the next slide there, Bill. If you make a note of your question, and if you want to do it along the way, you can post it on the chat, which is just there. We will try and come back to it at the end of the session by Bill. We are recording this webinar, so when we've finished, we will send around a recording and you can pass it on to your colleagues if they've missed it, or you can watch again. Next slide. So we'll be giving you contact details as well at the end in case you've got anything burning that you want to pick up with us on a one-to-one basis, and you can keep tabs on any future events on our website or LinkedIn. So without further ado, Bill is chomping at the bit to get going, and I'll just hand over to him and we can get into the bones of this.
Yeah. Well, good afternoon, everybody. It's great to be able to be here with you, and it's great to be able to talk about overhead lines, which of course has been my passion for many, many years. Well, perhaps I should start by explaining why I believe conductor sags and tensions are the crux of overhead line design. And I believe that the choice of any conductor will determine three basic design issues: structural design of supports, cross arms, foundations and stays based on perhaps worst weather loads developed. Secondly, maybe the height and type of structures based on maximum and minimum conductor sag. And thirdly, also importantly, the circuit capacity, the current rating based on the maximum conductor operating temperature, which is related to the maximum sag. Later in this session, we will be looking at a typical example of the role of sags and tensions when considering uprating a line. But before we look at that, we need to have some understanding of conductor design and selection. Clearly, the best option for a conductor would employ the smallest physical area to minimize weather loadings and the highest conductivity. Apart from excellent conductive metals such as gold and silver, the best practical solution would be copper, which was used extensively for many years, but is now very expensive. There was also a downside to copper in that it was very heavy, and being heavy tends to result in higher sags. A cheaper but less conductive solution is all aluminium. It's cheaper and lighter than copper, but it's only about 61% conductive compared to copper. So it's not as strong and can only be used for very short LV lines. Well, during the late 40s, a bimetallic solution was developed incorporating a stranded steel core within an aluminium conductor. And we call that aluminium conductor steel reinforced ACSR. Use has also been made of aluminium alloy steel reinforced conductors, aluminium alloy AAACSR, to increase the strength, particularly for some tower lines. These conductors can be used for long spans, but are, unfortunately, susceptible to corrosion even when greased. A better solution is a homogeneous aluminium alloy conductor that achieves a good balance between cost, strength, conductivity, and sag performance. However, all aluminium-based conductors will anneal or soften when the operating temperature approximates 93 degrees C, providing a cap on the operating temperatures that we can choose. The electrical losses for AC lines also need to be assessed.
So, Bill, the predominant conductors for both wood and pole lines would be ACSR and AAAC?
Yes, that's right. Yeah, very much so. But particularly historically on steel tower lines, they were either copper or more recently ACSR, and tending to become more frequent with aluminium alloy, whereas the wood pole lines generally are either very small ACSR, or people have generally gone over to aluminium alloy as a standard now.
Thanks, Bill.
Okay, there are some new designs of conductors which permit higher operating temperatures in excess of 93 degrees C, and they're known as high temperature low sag, HTLS conductors. These rely on a high strength core manufactured from high strength steel or carbon filaments. These new conductors operate on the basis that the aluminium strands will expand more readily than the core, and the mechanical load is then transferred to the high strength core only. A knee point occurs below which the conductor will operate as an ordinary conductor. That's both elements, the steel core and the aluminium outside of it. But above this knee point, the load is only supported by the core. And these conductors are designed to operate perhaps 150 to even 210 degrees C, depending upon the design. These new designs permit a higher current rating than historically, and hence can avoid a significant change to the original line infrastructure.
These are predominantly over tower lines, Bill?
Yeah, very much so. These are generally tower lines. I don't know of any that is used for a wood pole line, although there's no real reason technically why you couldn't operate a high temperature, low sag conductor on a wood pole line.
Mm-hmm.
So having considered the conductor medium, we need to turn our attention to the basic mechanism for undertaking any sag tension calculation. Now, this is a very simple slide, but it's a very important slide. And this is one thing, if you take away from this webinar, is what's shown on this screen, which doesn't seem like an awful lot, but it is really important. As a conductor temperature changes, or the applied stress acting on the conductor changes due to weather issues, the conductor length will obviously shrink or expand. The tension in a conductor varies according to the actual length of the conductor, and similarly, the sag is inversely proportional to that tension. It's important to note that a small change in actual conductor length can have a dramatic effect on tension and sag. For example, a typical 300-meter span of links conductor, that's an ACSR conductor, extended by 50 millimeters will result in an increase in sag of about 1/3 of a meter. And maybe a 120-meter span of aluminium alloy oak conductor will be extended by about 25 millimeters. If you extend it by 25 millimeters, will result in a sag increase of 1/4 of a meter. Now, this is important to note whenever you might encounter a broken conductor on site and it needs repairing, because it's important to ensure that the conductor is not accidentally re-erected with increased sag because the conductor's been lengthened, or conversely, a piece may have been cut out of that damaged conductor and the two ends put together, and you've got too high a tension in the conductor as a result. So the actual length of a conductor is so important in the design of any conductor sags and tension calculations that we undertake. Okay, as a conductor temperature changes, or the applied stress acting on the conductor changes due to weather issues, the conductor length will shrink or expand. A change in the span length, the operating, sorry, I'm getting a bit beyond myself here, variable parameters affecting sag tension design. What are these parameters? Well, there's a change in the span length, the operating temperature, the weather, the wind and the ice, and any restriction to ensure safe working loads are not exceeded during normal operation or erection conditions. And we'll look at the weather parameters a bit later and how that particularly affects it. As you can see, these things vary the tension and the sag, therefore, in a particular conductor. Okay, this slide indicates the basic means of calculating any line tension by considering a change in conductor length in a so-called change of state calculation. The temperature and stress changes are added to a known set of initial parameters, and the final conductor length can then be used to resolve the final tension.
Can you just give us an overview of those parameters, Bill? The alpha, the L, small t, large t?
Yeah, that's right. I didn't put this on the slide, but the alpha is the coefficient of expansion of the conductor. The length is obviously the horizontal length of the span in question. Little t2 and little t1 is the temperature change. T2 is the final temperature, T1 the initial temperature. And similarly on the stress changes, big T2 and little t1 are tension. A is the cross-sectional area of the conductor, and E is the modulus of elasticity. And putting all this together, as it shows on this screen, it's plus or minus these temperature and stress changes. You might have a temperature change which is increasing, but there may be a greater stress that you want to apply, and it will vary accordingly, and you end up with a final length. Okay. Now, this is just a little bit of maths. We're not going to go into this in great detail. The initial and final conductor length formulae are added as shown to provide an initial state and a final state. We're less interested in the actual conductor length here now, but since the tension is related to length, the calculation can be solved for final tension T2, and once this is known, the sag can be determined. Okay. Now, there are two broad methods that overhead line designers employ to determine line tensions and sags: parabolic and hyperbolic. The parabola is a simplified form of calculation which considers only the first term of the hyperbolic expansion shown in red. As it is pretty accurate for span lengths up to around 200 meters, all wood pole lines, you generally tend to use this method. The errors that they introduce are very negligible. For spans over 200 meters, thereabouts, the hyperbolic or catenary calculation is employed, as this is the most accurate, especially for steel tower lines, although equally it could be used for wood pole lines if required. And what I've done there is just to show the hyperbolic expansion of these, just to show you how the calculation can be undertaken, and showing that first term in red, as I've already explained. So far, we've seen the effect of tension and sag changes considering a single span. So how do we handle many spans within a section of line? Well, the supports along a line route may be of differing lengths, perhaps to minimize land interference or cross over rivers and motorways. And when the successive spans are of unequal length within a section of line, changes in stress or temperature will cause unequal changes in tension in the different spans. On tower lines, when conductors are finally clamped into their suspension shoes, the insulators are plumb. But a change of temperature or stress will tend to swing the suspension strings in the inline direction into an off-plumb position. On wood pole lines, this doesn't occur, but because they're bound into the pin or post insulators, but the flexibility of the supports need to take that out of balance tension that is generated. Although there will be, and that's where a problem where we use a single basic span, which is often the case with wood pole lines. And people tend to forget that if you use a single basic span for all wood pole lines, there will be out of balance tension loads on the structures caused by these differences in tension. To avoid this to a greater extent, suspension insulators being off plumb when the conductor temperature or mechanical load changes, it's often convenient to undertake sag and tension calculations in terms of a hypothetical equivalent span. The calculated tension applied to each span within the section of line between the tensioning points. As it says here, BS IEC 650 defines the equivalent span as a fictitious single span in which tension variations due to load or temperature changes are nearly the same as in the actual spans in a section. And you can see that at the bottom half of this slide that I've calculated the average span in a column and then the appropriate equivalent span. And you can see that simple changes in span length, 100, 110, 120, and so on, the variation in the equivalent span is not so great. But when you've got quite large variations, it can have quite a profound effect on that bottom line. got 5 spans of 120 meters and one of 202, and you can see that there is now a change occurring, and consequently there will be a tensile change within that section, and that's why we use the equivalent span to try and iron out those problems, those equivalents, those tension issues that otherwise would occur.
So just summarising, Bill, typically wood poles don't use equivalent spans, but tower lines do.
Yeah, generally speaking, that's true. And really, the problem is that if you don't use the equivalent span, you're going to end up with a permanent longitudinal out of balance load on structures, wood pole structures, which people tend to forget about. They don't normally consider them. If you were to use equivalent spans on wood pole lines, then you'd have to use stays at every section position, and that's not such a good idea. And that's why they've used a basic span, which equates to all the spans as the ruling span concept for the whole of the line. But it's going to introduce problems that you perhaps don't realize. Okay, so this slide just indicates that here I've calculated a 300 meter equivalent span, and you can see that there are some extreme span length changes, which I've shown in red, 235 to 338, over 100 meters difference in change. We don't want to, we can't calculate every single span for a conductor sags and tension as a ruling span in each case, and so that's why we put them into a line section. We treat them all those spans the same, using an equivalent span for our calculations. Okay, so let's look at a typical change of state calculation using a typical 175 millimeter squared Lynx ACSR conductor with a 300 meter equivalent span. Let's just look at that, what's that column that says case 1. Assume that the initial known state is 36,000 newtons at minus 5.6 degrees C in still air without ice. Increasing the temperature to a final state of, say, 50 degrees C will obviously increase the actual length of the conductor, as we've already discussed, and in so doing, the tension reduces. In this case, the tension will drop to 22949 with a sag of 4.15 meters. No great shakes there. I mean, that's pretty obvious what's going on there. And
just to stop you there, Bill, this sheet, this is a spreadsheet which has got the formula underlying, and the blue numbers is the starting point, and the red are the calculated.
Exactly. So within this spreadsheet, behind the calculation, we're doing that change of state equation. We're using the change of state equation. We're starting with 36,000 minus 5.6, and we're ending up with a tension at 50 degrees C. Okay.
Yeah.
So,
throwing you there.
Assume that the overhead line owner wanted to increase the current rating of the Lynx conductor, perhaps raising the operating temperature to, let's say, 75 degrees C. It would be important to ensure that the ground clearance infringements are avoided, so the maximum sag mustn't exceed that which was applicable for 50 degrees C. In this case, the initial tension condition remains at 22949 that we had previously, and obviously the sag remains the same as at 75 degrees C. But now the tension at minus 5.6 degrees C has increased from 36,000 up to 43,246. Again, the calculation is done behind the scenes, behind the software. And the owner would then need to check whether such an increased tension would be acceptable for the structure and any foundations, etc., etc. And this is a very typical scenario for most refurbishment projects. We'll have a look in a moment, or a bit later, a typical worked example. But this is the general idea behind refurbishing or repurposing an existing line and perhaps getting it to operate with either a different conductor or a larger conductor, maybe a hotter conductor. This same sort of procedure is used to determine what happens.
You've back calculated the limiting tension based on the previous still air tension and at 75 degrees.
Yeah. So this is a typical scenario, as I've said. So now we're going to have a look at, before we get into the calculations, the design philosophies that are used within an overhead line context. And there is a deterministic and a probabilistic approach. The deterministic approach is a broad weather loading design that dates back many decades and considers a single wind pressure and ice thickness that is applicable anywhere in the UK. Excuse me, my phone is just ringing. Sorry about that. Turn that off. Right. The publication of BSEN 50341 introduced a highly site-specific set of weather loadings that follows a probabilistic design approach. So there's two. We've got a single wind pressure and ice thickness for a deterministic design, or we have a very site-specific set of loadings that follows a probabilistic design approach. And this probabilistic design approach replaced a single set of weather loads for 3 load scenarios. Instead of just looking at wind and ice on a conductor, the probabilistic scenario considers high wind, no ice, wind in the presence of ice, and ice in still air. And in certain southerly areas in the UK, there may be economies to be realised for the probabilistic approach compared to the deterministic approach. A little later, we'll look at a worked example comparing these two design philosophies. But first, we need to be aware of the limiting loading elements on a conductor when in service and when being strung.
So deterministic, Bill, is the predominant method for wood poles and probabilistic for tower lines?
Well, yeah, certainly deterministic is used for pretty much all wood pole lines. That's certainly true. Deterministic and probabilistic are both used within the UK for tower lines.
Okay.
Yeah. Okay. So the deterministic design approach historically considers, in our case, 380 newtons per meter squared of wind pressure, which is roughly equivalent to a 56 mile/hour wind. And it's, but at the same time, it's on a conductor which has 12.5 millimeters of radial ice for tower lines and typically 9.5 millimeters radial ice for wood pole lines. The weather loading generates a maximum working or allowable tension within the conductor. The wind and ice loadings will also enable a designer to calculate the maximum longitudinal, transverse and vertical loads acting on the conductor, considering the conductor tension, projected area of the conductor seen by the wind, and the augmented conductor mass, respectively. These 3 basic loadings are essential for assessing the capability of all overhead line components. I just draw your attention to the photograph there. Notice the spiral accretion of ice, which is developed, in this case, as a supercooled water droplets are blown onto the upwind side of the conductor. And that ice load begins to increase the tension, and it thereby rotates the conductor, and a clear face of conductor is then presented to the wind, and so on, creating that spiral of ice.
So it doesn't build up on one side, Bill?
Oh, no, because it does, but as it does, the load increases within the conductor, the tension increases, and it begins to rotate. Yeah. Okay. Now, whether a deterministic or a probabilistic method is followed, there are a number of tension limits that need to be observed. Sorry, I just missed what I was reading. Need to be observed to ensure safety of the line and the line crew. Okay. So the first load issue to be addressed is aeolian vibration. It's important to ensure that a conductor is sufficiently slack to avoid the harmful effects of aeolian vibration that could, over a long period of time, begin to fret the conductor. And as stated, aeolian vibration occurs when a steady wind passes across a cylindrical shape and creates alternating eddies, which tend to excite the conductor in a vertical plane. To avoid conductor damage, a tension limit is placed on a conductor as shown. This vibration limit is often known as the everyday tension and occurs at 5 degrees C for wood pole lines and 15 degrees C for steel tower lines. Okay, and normally we consider that this concept of an everyday tension means that for the majority of the year, the line is not operating at a very hot in a very hot environment. It's not being blown about with lots of ice on it. It's just pretty much most of the day, most of the year, it's going to be roughly that sort of situation that occurs. Okay, any conductor that is erected needs to be safe during handling by line crews. And this slide indicates the safe working loads for come-along clamps and cross arms. And the maximum erection tension needs to reflect the lower safe tension of either of those two elements. It's assumed that the lowest practical erection temperature is 0 degrees C. And for example, the Lynx 22 kilonewtons is a safe working load that is found using a particular come-along clamp, and we will see that shortly. Another problem that occurs for an overhead line design engineer is long-term conductor creep. And as stated on this slide, creep is a function of increasing length of the conductor made of two differing actions, a geometrical settlement and a metallurgical extension. Now, conductor manufacturers will undertake a 1,000-hour test, that's a 6-week period, on new conductors that they are putting into the industry, and they undertake a creep test during that period of time, where the conductor is maintained at a constant temperature and the extension recorded on a daily basis. From this data, a predictor equation is derived by the conductor manufacturer, and the total extension over a period of 10 years can be calculated. The calculated creep can be compensated in a number of ways, but is generally by a specific percentage overtension to the design tension, or as a negative temperature shift related to the coefficient of expansion. So a typical conductor might result in a predicted minus 20 degree temperature shift. And in this case, linesmen would erect conductors assuming that the ambient temperature were 20 degrees below the actual ambient temperature. Okay.
So if that is taken into account, Bill, then the designer can disregard creep.
That's right. But of course, in doing so, he's had to marginally overtension the conductor. And so what happens is the conductor begins to sag over 10 years. And by the end of 10 years, you've reached your design sag that you first considered.
Yeah.
So you've eradicated all of the creep. Okay. Okay. Conductor load case limits. Now, from the previous slides, we generally have 3 load cases for tower lines designed deterministically, and they are maximum working tension. That's where we've got the wind and the ice acting on it. We have a vibration or everyday tension limit, and we have a maximum erection tension. And for probabilistic calculations, there would need to be 5 load cases to be considered. That's the everyday tension and the maximum erection tension, as before, but also now high wind, no ice, wind and ice, and high ice in still air, because we don't use the maximum working tension using probabilistic calculations. So let's look at a typical deterministic calculation for 175 millimeter squared links ACSR and the 3 load cases that I've already mentioned: MWT, EDT, and MET. And those are case 1, case 2, and case 3. I'll just draw your attention to case 3. You'll see it says there's that 22,000 newtons limit and a minus 20 degree C temperature. That means a 20 degree C shift.
Yeah.
Okay. Now we've got 3 columns. Now this is where it gets a little bit more complicated. It's possible to check whether the everyday tension or the maximum erection tension are overloaded. And this is inside the software. Now, what I'm trying to show here is the yellow column, the bright yellow column where it says MWT rules, is that tension rules with respect to the everyday tension and the MET, meaning that the EDT and the MET loads, the actual tensions, are lower than the actual numbers that we have permitted. So you will see that the EDT is shown as 14894, and that's lower than the 16,000, which is the vibration limit. So that's fine. And the maximum erection tension is 18551. That's also lower than, in this case, 22,000. What's going on here is a comparison undertaken by the software and making an assumption, in this case, that the maximum working tension rules, and checking out how that tension, what that tension would be at the everyday tension limit and the maximum erection tension limit. And in this particular case, the maximum working tension rules. Now, if it had not been that case, then the software then says to itself, well, maybe the everyday tension rules, we'll make that as an assumption, and we'll check and compare that with the maximum working tension limit and the maximum erection tension limit, and ensure that those limits are less than the allowable limits, the limiting tensions, which are shown in the upper half of the string.
So the blue values for each case, so maximum working tension 36,000, that's set by the conductor type. 16 is vibration, 16,000 is vibration limit, also conductor type, and the 22,000 that's your come along clamp for that conductor.
Yeah, the 36,000 is a maximum working tension, meaning it's not the breaking load of the conductor, it's a safe working load. In this case, normally it's a factor of safety of 2 deterministically compared to the breaking load of the conductor.
Mm-hmm. Yeah,
Okay.
and your software is looking, as you say, it's comparing, it's doing a calculation for each case for the maximum working, the erection, the EDT and the MET, and it's figuring out which one of those is worst case.
That's right. Yeah, very much so. And then once we've determined which of these 3 cases rule, in this case maximum working tension, we can then calculate what the tension is, in this case at 75 degrees C, shown in a red box, and hence the sag as well that's related to that, which is 8.41 meters in this case. Okay, so this is just, all this is showing is a comparison. We're comparing one case against another. And if this had been a probabilistic, and we'll look at that a bit later, then there would have been 5 cases, and we check one against the other, etc., and one of them rules. Okay, so just keep in mind that sag of 8.41 meters for Link's conductor. Now let's assume that this single circuit line needs to be uprated using, let's say, 300 millimeter squared UPass all aluminium alloy conductor. So it's a bigger conductor, it's heavier. I'm going to use pretty much the same limiting criteria. I'm using the same maximum working tension limit, which you can see up here, 36,000. And I've used this as a vibration limit, which is the breaking load of the conductor divided by 5, and also the maximum erection tension, come along clamp or cross arm allowable to me. And I'm trying to use the maximum working tension because I don't want to do any work on my towers if I possibly can. And so I've used this 36,000, the maximum working tension rules. It's just done that comparison check, so that's not a problem. But the problem here is that I've ended up with 2 meters greater sag than I started with. Remember that last slide, 8.41, it's now 10.42. So it's exactly 2 meters over sag, which obviously is unlikely to be acceptable out in the field, because there will probably be many ground clearance infringements. So what do we do? Well, the option here is to start from the other perspective and say, I want to achieve a sag of 8.41 meters at 75 degrees C, which I've done here. And I've done a back calculation and a comparison, the MET rules in this particular case, and the maximum calculated tension is 43952. Now that's acceptable with regard to the strength of the conductor. There we have that limit, 53,410. But I've got here now 43,000. That's fine, it all works. The difficulty is that it's exceeded the 36,000 limit that was initially placed on the Link's conductor. And as a result, it probably will mean that the tower, the foundation, the fittings on the line, etc., will all likely have to be upgraded. So that's a bit of a problem. Another option might be to assess the line assuming a probabilistic analysis. And what I've got here is an extract from BSEN 50341. Let's assume that the line in question is located on the Isle of Thanet, which is indicated with the blue stars. The maps show various contours. The one on the left shows the wind speed, the mean wind speed, and the one on the right shows the ice contours. And note that there are 2 numbers for the ice contours. The value outside the brackets is the still air radial ice accretion thickness, whilst the value inside the brackets is the ice accretion thickness in the presence of wind. And now I'm extracting this. This slide, noted on this slide are the applicable values taken from the weather map. The probabilistic designs consider a range of partial factors rather than factors of safety. And in this case, the selected partial factor for the environment is 1.1. It's a survival factor, if you like, and it's been selected as a because this particular line, let's say, is near to roads or railway, where you want an increased degree of security. So it's a security limit as well. And a 1.1 has a notional once in 500-year return period event. In other words, it's unlikely that you're going to see the ice and the wind exceeding the design loads at all. Lines out in the middle of nowhere, in across country and so on, you can use a factor of 1 for those particular situations. In our case, it's in very built up area, let's say, and we've used a factor of 1.1. And as for the deterministic assessment, we've considered this line strung with 3 UPass conductors plus an earth wire. Now, I don't expect you to go through all this, but these are all the differing parameters taken from the BSEN 50341. And the sort of things that are included here is the design includes the site altitude, obviously, because the maps were based on 0 degree altitude, i.e. sea level. In this particular case, yeah, we need to include a site altitude, and I've included, say, 100 meters there. Mean conductor height above ground, wind direction, which is normally taken as normal to the line conductors. The type of terrain, whether it's a rough terrain with hedges and buildings, or smooth ground, where flat ground, no obstacles. A partial factor on the strength of the conductors, which is normally taken as 1.25. And there's also the number of conductors that themselves are also included. In this case, there are 4, the 3-phase conductors and the earth wire. And this will give some degree of weather load diversity. Now, what that means, it is unlikely that you're going to get all 4 conductors full with ice loading for the whole of the span. And so therefore, there's a degree of diversity in the loadings that are given for that. So we gain a little from that. And once we've done that, the software will trundle out a number of answers. Here we have the high wind without ice. It gives me 716 newtons per meter squared. Just running through these fairly rapidly. We've got the low density but high accretion ice, 41.5 millimeters of ice at -10 degrees C. And then we've also got the wind and ice, which is showing 460 newtons per meter squared of wind pressure and just under 4 millimeters of ice. So now we can put all these results into a sag tension calculation along with the everyday tension and the maximum erection tension. Now, this looks extremely busy, but it's exactly the same as we started with this afternoon. It's all based on the actual length of the conductor, and it's a comparison between each of these different cases. All that's happening is we're checking to make sure that these limiting cases are lower than the permitted values, which in this case is the high wind, high ice and wind and ice loads is the braking load divided by 1.25. We've got our erection tension limit and the maximum, the everyday tension limit there as well, the maximum erection tension. And again, maximum erection tension rules in this case. And we've got 8.41 meters of sag, same as links, that's great. And we've got those loads that are shown in the red box. But there is a problem. In this particular calculation, because of the high ice situation, 41.5 millimeters of ice, as I calculated, at -10 degrees C, we end up with more sag at a heavy ice condition. In this case, it's 9.4 meters. And we've only got 8.41 meters for the hot condition. And therefore, strictly speaking, we have 1 meter of oversag for still air ice condition in excess of the basic sag. Now, it might be that remember when we did our calculation deterministically, we said, well, there's 2 meter over sag using UPass compared to links. Here we've got 1 meter over sag, and it may be possible to be resolved on site using suspended tension insulator sets for critical spans, and that will overcome the problem of the over sag. Well, certainly it's going to be better than the 2 meters that we had previously. Finally, we can determine the effect of employing a probabilistic design assessment for a UPass strung line compared with our earlier deterministic assessment for the existing links conductors. You can see that the ultimate longitudinal tension and the transverse loads are lower than for the deterministic assessment, whilst case 2A, high ice, results in marginally increased vertical loads. However, any strengthening or remedial work will likely be minimal for this probabilistic assessment.
So just confirm, Bill, the links, the value shown for the links, those were determined in a deterministic calculation.
Yeah, with a factor of safety of 2.5, which is what you use for a deterministic line design. Yeah. And so, yeah, I'm comparing that with the well, it's not called a maximum working tension. It's the maximum loading tension for UPass with a reduced factor of safety of 1.25. And you can see, although we started out with 63,000 compared to 36, we now have 79 compared to 90. So it's lower. So that's good news.
Yeah. So why a structural assessment?
Well, it's still going to be necessary because you can see, as I said, the UPass case 2A has an ultimate vertical load 66.5 newtons per meter compared to 49.33 for the links. So therefore, there is a higher vertical load on that structure, on the cross arms, etc. It's very marginal, but it will need to be considered, that's all. Okay, so let's just remind ourselves that these were the loading results assuming a deterministic assessment for UPass whilst matching the existing links sag values. Okay, and had we considered a deterministic assessment only for replacing links with UPass, it's likely that a greater degree of strengthening would be necessary. You can see all 3 of these loads are greater. We've got a greater line tension, greater vertical load, and a greater transverse load. Therefore, there's much more likely to have some greater degree of strengthening if we consider just the deterministic, and therefore there are some economies that you can make with a probabilistic design, depending upon where you live in the country. Not all places can benefit from that, but it's very, very specific, site specific that we're looking at, rather than taking a broad brush assessment of a single wind pressure and a single factor of safety. We're looking at microclimate areas, as it were, within the UK, considering a whole raft of different features or functions of the topography, etc., to achieve that result.
Would you, I mean, could you say that in general, it's usually more economically efficient to do the probabilistic design compared to deterministic? Is that
only in the southern part of the UK. You wouldn't be able to get away with it in the northern parts because the loadings are so great. And I understand that one of the DNOs is currently looking at assessing whether these ice loads that are given within 50341 are realistic and whether any economies can be made, because they are too onerous, really.
Yeah.
Well, I think that's it, really. I think I hope you found that presentation of interest and has satisfactorily addressed the statement that conductor sags and tensions are at the crux of overhead line design. Thank you.
Excellent, Bill. Well, I hope everyone's stayed with us there, and Bill took us through a really detailed example of how probabilistic and deterministic approaches are used in overhead line design. We've got a few questions that got raised, a few points. I'm just going to go through them. Bill, the first one I think was more of a statement there from Scottish Power Spend that they're working on a design for a CCR on wood pole Trident 132 kV lines.
All right. Yeah, very good. ACCR is an aluminium conductor core, a composite reinforced, and it's, as I understand it, it's a very expensive product. I believe it's made by 3M in the States, but in certain circumstances, even if it's very expensive, it can make various economies, I'm sure.
Next question came in from ESBN. This was more on the LV. It was about restringing LV lines with larger conductors. Where Tony is posing here. There's scope for, going to a 120 mil. I'm assuming this is ABC, or 150s or 75 copper, but the availability of 150 aluminium or 75 copper is a problem. I think we've been doing some work on this recently, Bill. I believe we've seen some 150
and 185. If it's ABC, you can go up to 185. I know that Northern Power Grid apparently are using that.
Yeah, so I think we have seen reference to 150s and, as Bill said, 185 aluminium on LVABC. A question about the deterministic approach and the development there we showed for links. In the tension, does it make a difference how fast the temperature will increase?
Well, I think that's a function of the weather, really. If it's freezing one day and it becomes hot the next, no, I don't think there's any reason. I mean, the conductors are designed for a raft of temperature changes. So how fast the temperature changes is not as far as I'm aware, there is no factor or problem with that.
So this is a interesting comment. Using probabilistic in light of climate change will be difficult. That's the first point. And reference to here the French using this approach, and then in 2000 got caught with some unexpected storms. Any views on that, Bill?
Well, I think going forward, I think we're seeing from the weather perspective in this country that generally icing loads, although they're dramatic, they're not so prevalent as they were. And I think ultimately we may find that you get very stormy conditions, but maybe less ice being accreted on the lines. And there may be some mileage in, as I say, reviewing those icing loads that are currently within the maps within 50341, because they're not really sensible values.
So in probabilistic approach, Bill, why not look at the high tension, low sag conductors as a solution? Does that help the prop? Does that help the?
Yeah, absolutely. Yeah. The only issue that I would suggest, though, is ensuring that the starting point, if you've got a conductor, let's say a line, an existing line, and it's operating at 50 degrees C, then you want to make sure that if you're going to use maybe a larger HTLS conductor, you want to make sure that the knee point temperature is above the temperature that the conductor, the original conductor is installed at, because what you don't want is to have any oversag that you're not going to be able to get rid of. So in other words, if you've got a heavy conductor up to the knee point, it's going to operate as an ordinary conductor. So you're going to get an oversag. Beyond the knee point, where you've got all of the load acting on the steel core, then obviously compared to the existing original conductor, that's not an issue. So yeah, it's a matter of ensuring, making sure that that at no point during the conductor temperatures that you've got any oversag occurring.
Okay.
You're going to use that.
Just a few more questions.
Yeah, sorry. It's just the only reason I used UPass here against links was just purely for simplicity. Yes, it's quite valid to be able to use a high tension, low sag conductor instead. Okay.
Just last few questions before we wrap this up. It's coming to our hour. Some people are beginning to disappear. We will record out to the end. If you're using a fiber wrap, which is common on tower lines, does this have an impact on the ice? And obviously it will have an impact on the calculations, Bill?
Yeah, absolutely. Yeah. What generally is undertaken is to consider an equivalent load. So you work out the area of the fiber wrap, you consider the wind area, etc., and if you're doing the calculations, sag and ten calculations, you'd add the wind due to the fiber optic cable and the mass due to the fiber optic cable and any additional ice which may be building up, and put that into the sag tension calculation. So yeah, it's the same thing, not just for a fiber wrap, but maybe aircraft warning spheres. They also will increase the load on earth wire normally in that case, and that has to be taken into account, the area and the mass and any ice that might build up on that, and make that as an equivalent load on a bare conductor or an already ice load conductor. You're augmenting an additional load along the whole of the line span.
Okay.
To be able to do the calculation.
So probabilistic designs on wood pole lines, feasible? Absolutely.
Yeah.
Not common.
Not common, but yeah, it's possible to be able to do it. But yeah, long as you can agree with the loadings that you get in your particular part of the country.
And then the last question there: why did you not use the probabilistic approach for links to compare with the UPass on the same base?
Because I'm just showing the difference between a deterministic approach and a probabilistic approach. That's all. It's just a typical scenario. I mean, yes, you're quite right. There are other options that I could have considered.
Okay, Bill. We're all done there. Just the last slide is showing just if you just move ahead there, we'll just give people the contact details. If they want to email, they can email me. I can absolutely. If there's any questions for Bill, just send it to me. We're planning to hold some formal training in the autumn, and we will send details of this to anybody who's registered or attended this webinar. And if you want to avail of that, then just stay in the loop. Absolutely, forward any queries you've got. And last but not least, thank you, Bill, for the very comprehensive overview there. And I hope everybody enjoyed it. I hope you've learned something and maybe got a few pointers. And until next time, take care and have a nice weekend.